I want to make a video to review chapter 9, and the main focus in chapter 9 is immunization and duration. Duration is a measure, and in immunization, when we talk about immunization risks, we're gonna use the terminology duration, use the concept of duration. We will do present value matching and duration matching when we are talking about um, immunization. So this is a some of the main topic we will be focusing on in chapter 9. We don't have enough time to go over every single topic in chapter 9, so we're going to focus on 9.1, 9.2, 9.3, and 9.6. All right, let's start with the overview. In chapter 9, we're going to focus on interest rate sensitivity, which the main reason is to talk about immunization. This is not the medical term immunization. It's a risk mitigation strategy. And when we're trying to apply technique of immunization, we'll talk about how do we match asset and duration. Okay, so let's start with terms. First, liability. You can think of liability as future debt. For example, suppose you are obligated to pay 50,000 5 years from now, like for education or for other reasons. That is a liability. To cover this liability, you have to do some planning now, just so you will have enough funds in the future. So one of the ways to cover that liability, suppose the prices for 5-year coupon bond are not as so we're comparing to investments, 5-year zero coupon bond and 3-year zero coupon bond and 7-year zero coupon bond. So we can combine we can make a portfolio of different type of investment to match that future asset that we wish to have to cover the liability. Um, all right, so here we have a condition. Suppose the prices for the 5-year zero coupon bond are not so good. So you consider if there's better prices for a different maturity, maybe they have better price, like lower price. Then you might use other type of bond to combine and having the same future value as the future 5-year zero coupon bond, but the combined portfolio maybe have a better price. Okay, so as a little expansion from that idea, so here ideally you should buy the 5-year zero coupon bond because the future value of 50,000 is what you wanted. But suppose we have some other bond has better value, like lower price now. Okay, so this is the idea of using different type of investment to pay for future liability, and maybe in the variety of investments, some of them may have better value than others. Let's talk about the notion of immunization. And this was explained in the book by example. So if you invest for less than 5 years, you hope for a higher rate. Um, so for the one, if you're using 3-year zero coupon bond and 7-year zero coupon bond to create the portfolio that has the same cash flow as 5-year zero coupon bond, then the 3-year zero coupon bond mature earlier than 5, so you have to reinvest it, and the 7-year zero coupon bond will not expire, and you might have to find its 5-year value. So there are different consideration. Okay, so like it says, you hope for higher rates for investment time because you are giving money, you're buying the bond, and you are hoping for a higher repayment payment in the future. So this is investment. As investor, you're hoping for higher rates. um, I guess we talked about it before. If you borrow money, you're hoping for lower rate because you were supposed to pay it back, and of course, lower rate is in your favor. If you're investing, you certainly will hope for higher rate. Um, and it's different as far as the cash flow. If you are investing, you have negative cash flow now, but positive cash flow in the future. If you are borrowing, you have positive cash flow now, but negative cash flow in the future. That's so we certainly will always hope the rates will give a benefit for the one that we have a positive cash flow for the part of cash flow. Um, so it's natural to wonder whether there might be some way that you could split your investment buying 3-year zero coupon bond and 7-year zero coupon bond. So combining these two type of bond is a portfolio. So in that portfolio, certain portion it goes in the 3-year zero coupon bond, certain portion goes in the 7-year zero coupon bond. What portion, what kind of distribution is it? There may be a better or best plan, and we want people to determine the best combination of the two types of bond. And this idea is the idea behind the immunization strategy. All right, number one thing is if you have a 5-year liability in the future, you would try to make sure you have that kind of cash flow. So your investment has to match the liability cash flow. So your cash flow in your investment gotta match the liability cash flow. So this is it's called asset matching. Okay, we're gonna start with the example on immunization. Suppose you need to pay 50,000 in 5 years, and then you can finance this with zero coupon bond. So this is matching the example we're talking about before. Imagine you buy a 3-year zero coupon bond with 22,675.74 redemption amount and 7-year zero coupon bond redeemable at maturity for 27.562.51. And you can see if you combine the two redemption price, the total is that 50,000. Each one of them is priced to yield 5% annually. Suppose also that at the end of the 3 years, no matter what the yield rate may be, you sell the remaining bond at a purchase price to yield I, combining the proceeds with 22,675.74 from the redeemed bond and use the total. Okay, so basically the 3-year zero coupon bond is your cash flow at time 3 at 3 year. That's for the 3-year zero coupon bond. But the 7-year zero coupon bonds did not expire at time 3. So we would reinvest mature the redeemed value of 2267.74. We should be able to leave the non-expired 7 years zero coupon bond in there to buy 2 years zero coupon bond. All right. So this is different than what originally planned for. This is actually redeem or sell the 7 year zero coupon bond at time three, even though it hasn't expired yet. So we sell and combine that proceed with a 22,675.74 since that's a maturity at time three. That mature at time three, we do have that cash flow. So combine them and buy a 2 year zero coupon bond instead. Illustrate that this immunization against interest rate risk by showing that it produced a need of 50,000 5 years after the initial bond purchase. If the interest rate is 20%, 5%, or 1%. Okay, so we're gonna try to illustrate that this method actually immunize against interest rate risk, since for different interest rate the outcome is the same. All right, so how do we know that? So we were supposed to do calculation for I equal to 20, I equal to 5, and I equal to 1%. So let's start with I equal to 20%. In that case, the original 7 year bond, since it's got a zero coupon, we will be able to find its value at time three. It still have 4 years until maturity, so we're gonna have to discount the 27,564.71, discount it to its value at time three. We discount it for 5 year. We will have that value, and that value combined with the redeemed value of 22,675.74 is the cash that we had at time three. Then we're going to reinvest it for the interest rate of 20%, and then at time five, we'll have 51793.75. Okay. So we cover the liability of 50,000. We have a little more cash left. Then second case, if I equal to 5%, then again we will discount the future value 27562 with 1.05 to the power 4. Then we have the actual cash flow at time three combined with the original maturity value of the 3 year coupon bond, 3 year zero coupon bond. So this is our value. And then we're going to reinvest it. So we let it grow for 2 more years. At time five, we have this. But still with lower interest rate. As an investor, when the interest rate is lower, we obviously have lower future value. And I still verify that higher interest rate for investor, higher interest rate provide more value of the investment. Now, last one, if I equal to 1%, then discount a future value to 7, which give us more money. And then we add with the maturity value 22675, and then we invest it at 1%. We have 50,150, and that also has, interestingly, it actually have higher value than the 5%. I wonder why. I guess the discount factor. When you discount something, lower rate is better than higher rates, but when you let money grow, higher rate is better than lower rate. So these are the first example. And all right, we're gonna try to think about the reason for this. So for a fixed set of cash flow, let PI, let's talk about notation. PI denote the total price, P as capital letter of price, using compound interest rate of I. So price is a function of the interest rate. And this is called a price curve because price can be affected by the interest rate. And this could be a price for your portfolio. Now, duration. Duration of a set of cash flow is a measure of how sensitive the price of the portfolio is to a shift in the interest rate. So how sensitive it is, or I guess one of the things we can do is to find the derivative of the price function with respect to I, and that's derivative. The first derivative will be a rate of change, which also could be a measure of how sensitive the price is to the interest rate. If the price, that's a calculus perspective. If the portfolio has a duration 5, then for a small h, it will lose about a fraction of 5h of its value if the annual effective interest rate goes up from I to I plus h and go up in value by approximately the fraction of 5h of its value if the interest rate decreased to I minus h. Okay, this is the duration equal to 5. So sounding like the duration is a negative of the slope because if duration equal to 5, it will lose 5. If the interest rate go up, it will go up by 5 if interest rate decrease. So there's a negative relation there when the duration is 5. So you can think of the duration as negative the first derivative. Modified duration captures the rate of change of the price relative to the price. So it sounds like we could define the modified duration as a derivative of the price function with respect to the interest rate. Asset liability management. So we're going to talk about immunization. Asset liability management refers to the technique for maintaining a firm's ability to meet its cash flow obligation in world of changing interest rate. Tools used to counter interest rate risk include immunization procedures such as Reddington immunization and full immunization. Both of them are terminology I wish us can study. So let's look at the definition. Reddington immunization focus on small interest rate shift while full immunization address arbitrary parallel shift of a flat yield curve. For Reddington immunization, you structure your holdings so that the assets and liability have equal present value and duration, while the convexity of the asset is greater than the convexity of the liability. The immunization in example 9.1.1 is an example of full immunization. So the example we just talked about earlier, it is an example of full immunization. Okay, but we haven't really defined it. But Reddington immunization involves matching present value and also matching the duration. So we match two of them on the condition that the convexity of the asset is greater than the convexity of the liability. We can think of the convexity as a second derivative of the price function. All right, so let's start with the second example. Let's look at asset liability matching. Sandy is obligated to pay 10,000 in 6 months, 15,000 in 12 months, and 25 in 18 months. He wishes to purchase bonds to exactly match these liability. That is to provide inflows so that the net cash flow at the 3 payment time as well as all other times is 0. The bond available for purchase by Sandy are of the following three types. 6-month zero coupon bond sold to yield investors 6% nominal interest rate convertible semi-annually. So if it's convertible, we're going to take the 6% divided by 2. So the 6 months interest rate is 3%. 12 months, 6 months par value bond with semi-annual coupon. So that could match the 15,000 cash flow we wanted as 12 months, 18 months, 5% par value bond with semi-annual coupon. How much of each of these should Sandy purchase, assuming that each may be purchased for any par value that Sandy would like? So in this case, we need to match the liability with the assets. The liability is listed in the first sentence, and the asset we're talking about are those three types. So number of each asset we need to purchase should be matching the liability that we had at three different time points. So we're gonna first figure out how much of this. It sounds easy, but it's not that easy. So there's always remaining value for each asset. So first we're gonna figure out how much of these 18 months bond to purchase to match the 25 obligation, since the other type of bonds will not help with this liability. So number one, the 25,000 in 18 months, we're gonna have that. Did that one have the 18 months 5% par value bonds with semi-annual coupon? So we need the maturity to be 25,000, but we also have the 5% par value bond with semi-annual coupon. So the coupon rate is 5%. So let's look at if we purchase the face amount of FC of the 18 months bond, then Sandy has the right to coupon payment of 0.025 times the face value every six months, and also to the redemption payment of FC. Therefore, at time 18 months, he stands to receive 1.025 of the face value. The total from the time 18 months coupon payment and the Reddington payment, redemption payment, setting this equal to 25,000. So we set 25,000 equal to 1.025 times the face value. So the face value we need to buy of the last bond is 25,000 divided by 1.025. The answer is 24390 of 24. That's how much we have to purchase of the last bond. All right, now what do we run to nearest penny, so the face value is 24390.24, and the coupon payment every 6 months will be 609.75. Okay, so now that we already have cash flow, I guess we can start looking at the cash flow now. It's gonna look like this. So with that, we figure out that if our timeline, start with 0, and then we have 6 months, 12 months, and then 18 months. We wish the 18 months to be 25000, and that is equal to 1.025 of the face value. And turns out the face value is equal to, after the computation, after the division, the face value is this much. So with that face value, we calculated the cash flow at every 6 months. So now we have this according to this last bond that we suppose purchase. We have this cash flow and 609.76 this cash flow, and the last one is a combination of the face value and the coupon. All right, so now we are looking at trying to figure out the other two bond, and we wish to receive a total 15,000 at time 12 months. So at time 12, we wanted to have this much. And since we already are receiving this much coupon, the additional 12 months bond we have to purchase is this much. So what do we do? The time 12 is the expiration for the second bond. At expiration, you would receive the coupon and the face value. So let's call that face value for B. And using this, you'll be getting the face value for the second bond And that is, I did draw when I was teaching it last time. Okay, so it looks like after the subtraction, this is a face value, this is a cash flow for the 12 months bond. All right, with that, we divide both sides by 0.03. We have the face value, which is 13.971.11. So then that's how much cash flow we were supposed to buy. So within the blue FB value is how much we would buy the 12 months bond. And then that also causes a coupon for times 6. So the times 6 coupon would be the 10,000 minus the, we already have a coupon from the third bond. And then we also have a coupon from the second bond. So 10,000 minus 609.76 minus the 419.13, since that's the value of the coupon. And then we have a leftover, which is after the subtraction, which is the 8971.11. Yep. So that's how much we should buy for the 6 months bond. And that is, in fact, since it's a short-term bond, I believe that one has no coupon. 6 months zero coupon bond, 12 months has a 6 months par value coupon, and the 18 months also have coupon. The first one has no coupon, so then all that there is that face value is the face value we were supposed to buy of the first bond. All right, so that is the solution. The one that block out FC, FB, and FA is our answer for the portfolio. As you can see, we solve for FC first, and then solve for FB, and then solve for FA. That's the progression of reasoning. So this is a example on asset liability matching or immunization. All right. Before we talk about immunization further, we have to talk about the terminology duration. So we have to define duration and find out way of calculating duration. Then we're gonna go back to the idea of immunization. And we did talk about duration a little. Modified duration is actually the derivative of the price function. And here we go. So, and the one of the important concept that we just did is present value of the set of cash flow. And we assume that accumulation is by compound interest. We add two assumptions. First, we assume a flat term structure of the interest rate. That is, we're assuming the interest rate did not fluctuate. We're assuming the spot rate are all equal. And that is assumption that may not be true in real life. Second, we assume if one spot rate changes, all other spot rate change by equal amount, so that we again have a flat yield curve. Okay, so assume that if the interest rate change, we assume they all change the same amount. All right. So let's look at the present value, the price of a cash flow. Suppose you said you have a set of cash flow CT. T is a time. And we're assuming there are only finite of C. We're assuming that they are all non-zero. We're assuming you have a 0 that represent initial time. All right, so PI is representing the price of this set of cash flow, the present value of the cash flow. So T times 1 plus I to the power of negative T. This is a discounting all future cash flow to the present time. And this summation gives you the total present value. This is the price curve. So we're talking about present value. So it has a negative correlation with the interest rate. If the interest rate is small, then after you discount it, just look at one of them. If think about summation is more complex, just think about one single function. 1 over 1 plus I to the power of -2 or power of -3. That is a negative power, so when it's a reciprocal function, so that definitely have a negative correlation with I. Whenever the I increase, then 1 plus I to the power -t would decrease. That's why the curve is a decreasing function of I. So price curve is a function of interest rate. Interest is a independent variable, price is a dependent variable. Okay, um, the price function is an infinite differentiable function. It is a negative power function, so you can always differentiate it. If you find um, the Taylor expansion of pi, then 9.2.3 will be the Taylor expansion theory of the pi. So basically pi and 9.2.3 will be the same thing if the Taylor theory converge. I hope that kind of bring back some of the memory that we had from calculus. Now, if we keep the first two term, pi0 plus pi prime I0, I minus I0, you see that is a linear approximation of the function pi. If I0 is close to I0 is with like a approximating point. The Taylor theory is expanded at point I0. So this is a tangent line function expanding tangent line of the function pi expanded at I0 point. So 9.2.4 would be approximation function for pi. 9.2.5 is approximation function of degree 2 of pi. Ideally, the one that has higher power, a degree 2 approximation should be more accurate than degree 1 approximation. A little review of calculus. So now we can also find the derivative of a function if the function has a Taylor expansion, has a theory, a power theory expansion. So pi can be represented as summation of ct times 1 plus I to the power -t. If you find the derivative of this function using the power rule, you are getting 9.2.6. If you find derivative of this function using the power rule, you will see 9.2.7. Now, why are we talking about it? Part of it is that we have pi and pi prime in 9.2.4 and 9.2.5. So maybe we wish have a value of the derivative, first derivative or the second derivative. So these are a little review of the calculus concept and how they relate to what we're talking about right now. And we'll come back to this once we look at a couple examples. So this is example 8 for 9.2. Excel Finance hold loans that guarantee they receive a repayment of 1,000 in 1 year, 1 million in 1 year, 2 million in 2 years, and 2 million in 6 years. They also have issued bond that require them to make payment of 300,000 at the end of each of the next 3 years and 3 million in 4 years. So the first three cash flow are positive cash flow. The 300,000 and 3 million, these are they need to make payment. These are negative cash flow. We calculate Excel Finance's price function at 2%, 4%, 4.9%, 5%, 5.1%, 6%, and 10%. Then use the tangent line approximation at I equal to 5% to estimate the price at each of these rates. Excluding 5%, also use the second Taylor polynomial around I equal to 5% to estimate the prices. Okay, so this is applying the notion that we had earlier that we could use a degree 1 approximation 9.2.4, and we could also use a 9.2.5 as approximation. But if we are doing this kind of approximation, we need to know the value, the first derivative, second derivative, and pi, of course. Okay, so to do all that's required of us, we need to know the price function first. All right, so given all these ideas we have, you can see, and we can set up um, the timeline to look at the cash flow. Okay, so one, 1, 2, 6. So we got 1, 2, 3, 4, 5, 6. All right, according to what so the time 1, we need to receive payment. So this is positive cash flow. Time 2, 2 million, and time 6. Okay, and we also issued not require them to make payment of 300,000 at the end of each of the next 3 years. So here is billing, and that's payment, so negative cash flow. Okay. Um, and in 4 years, it's 3, not 4. These are negative cash flow. At the end of each of the next 3 years. Maybe I misunderstand it. 3 years meaning that this each of the 3 years. This is negative cash flow. Each of the next 3 years uh and time 4. Okay, calculate the price function for all these. So first we're gonna set up the price function. Since those are clear, and this is what we intend to do first. Try to clear out the page here. Now that we're clear with the cash flow, so we're gonna see the differences of the present value calculation. So you get a 1 million minus 0.3 million, which discounted for 1 year to get the present value. 2 minus 0.3 million to get the discounted for 2 years to get the present value. So with all that, we're able to start looking at the solution. All right, so liability and asset, it's being called that. So this is the 1 million minus 0.3 million. this discounted for one time period, 1 year, and then 2 minus 0.3 million discounted for 2 year. And then once you have the timeline, you can see it. For time 3 is there's only negative cash flow. For times 3, negative cash flow. And then time 4, there's only negative cash flow. And then there's a time 6, there's a positive cash flow. So with that positive cash flow there, right? That's how we set up. So just so we can be clear of the price function, PI is given here. So now we can calculate for different different value of the interest rate I. We plug into this function. We're able to get the value, and you can see all these values. And we've done the first assigned answer the first assigned question. So you can see for as far as the present value, if the interest rate is lower, then the present value should be higher. Then if the interest rate is higher, then the present value should be lower, such as for the 10%, the present value is actually lower than the rest. Right. You can also use the net present value key PA2 plus calculator. You're going to add all the cash flow that we just mentioned in the question. C1, C2, C3, C4, and C6. You gotta make sure C5 equal to 0 because you can't skip. They're all equal amount of time in between these cash flows. You cannot skip. And that allows you to calculate the present value. Okay, so this is how to use BA2 plus calculator to do the same calculation that we just mentioned here. All right, then there's this task we didn't talk about. That is, once you got all these price functions, value calculated, we're going to use a tangent approximation to calculate the price again. For that, we need to know the derivative, and the derivative should be able to calculate with this. Or you should find the derivative of the price function. Price function is already in here. So for that, we would do, it's not given here. I think I might have skipped that part. All right, actually in this part, point 5, we move on to talk about relative price change. Using the formula 9.2.9, we're calculating what's called a fractional price change or relative price change. PI minus PI0 is new price minus old price. That's a price change. So you divide it by PI0, that gives you the price change relative to the old price. That gives you the fractional price change or relative price change. Another way to write the approximation is 9.2.10. The relative price change divided by I minus I0 will give you something close to P prime over PI0, because you see PI minus PI0 divided by I minus I0 is a rate of change. Average rate of change from time I0 to time I. So that rate of change should be similar to the derivative value of the price function. So what we were doing, the last example was 9.2.8. So the next example, we're gonna use the formula 9.2.9 to approximate the price, the change of the price from I equal to 0.05 to I equal to 0.051. So we are going to do the same calculation in the formula of 9.2.9 using the example that we just did. All right, so to calculate 9.051 minus price at 0.051 minus price at 0.05 divided by price at 0.05. since we already have those price already calculated and they're already in the page here, I guess we could use these as our value in our computation. You can certainly use the number that's already in here. So this is our price function. In the price function, if you plug in all these I values, you will be able to, this is our I value. You'll be able to find the price I, PI, and the PI end up being all these number. I skip the part that how do we enter this into the calculator. I guess the easiest way is to set up the function and then plug in the I value into the function. This can be done using your calculator or use a computer. Okay, so there we have it. We're gonna need the one for I equal to 0.05 and I equal to 0.51. That is the fourth one and fifth one. So 1, 2, 3, 4. That would be, this one is for 0.05, P 0.05. This is a P 0.051. And that's kind of the source of the information in the solution. So moving on to this calculation that we just did. So we subtract them and divide and we get the relative change of price. Now that relative price change, if we wanted to find the change, you multiply it with the price. Price change. So we're gonna do what is being identified at 9.2.10. We're trying to approximate the price change. So up there we calculate negative 0.005 is relative, it's called a relative price change. And this question is to calculate the relative price change. Okay, so the first one is the calculation for the relative price change. The second one is using 9.2.9 to estimate this change. So we're using the derivative to calculate the price change. In the bottom equation, the numerator is a derivative that is a p prime I0 divided by p I0. So the negative 1957398, that is a negative, that's the derivative pi0 divided by pi0. I0 is a 0.05, and then we multiply the subtraction of 0.051 minus 0.05. That gives us negative 0.0501, which is pretty close to the true relative price change. All right. There's a reason that we are studying the relative price change, because the way we define modified duration, you can think of the modified duration as the negative of the derivative of the price function divided by the price function itself at point I. Now we have formula for P prime I and we have formula for PI, as we already mentioned here in this page. So applying 9.2.6 and 9.2.1, we're able to model PI and P prime I. With that, we're getting 9.2.13. And this is a calculation of the modified duration if the nominal interest rate is I. All right. So this is called DI1. The one in the notation, this the one representing convertible one time per year. So we would use DIM if it's convertible M time per year. Okay, so just try to figure out what was the meaning of the notation. So if we have the IM, and then we would do negative dp over relative derivative dp with respect to IM divided by pi. IM is the annual effective interest rate. Then the IM, it's actually the nominal interest rate. I is the annual effective interest rate. All right, with that, we have, according to chain rule, dPIM equal to dPdI, di, dim. And di, dim, using the formula for I, we have we have this formula. And because of that process, we're able to have a formula for dPdIM. All right, combine that into 9.2.4. We come up with 9.2.15. All right, so then we end up getting di1 times 1 plus I, and they're equal to dim times 1 plus Im over m. So then dim times 1 plus Im over m is independent of m. As you can see, the left side and right side of the equation 9.2.15 have very similar meaning. And we can also define di infinity. That is when you are using continuous compound model. In that case, we will be able to figure out the continuous compound model, and then the compound rate is delta. All right, the one that we just calculated, we gave it a special name. We call that Macaulay duration. I guess this really goes to the fundamental idea of Macaulay duration. Since the left side and right side of the equation for compound one time and compound m time has very similar format, then define it, it makes sense to define this by a single term called Macaulay duration. So Macaulay duration equal to di1 times 1 plus I. I guess that's the most common way to calculate the modified duration. So di1 is modified duration, di1 times 1 plus I is Macaulay duration. Think of Macaulay duration is when you have no consideration of the number of compounding per year. Okay. Um, So the formula here involves derivative, and if you have at the finance classes, you may see that we are calculating Macaulay duration. We don't exactly calculate the price function's derivative. So a formula that involves derivative might be harder um, to to work out in the actual question. So we want a way that does not involve the derivative notation, even though it is really the negative the derivative function divided by the price function. So we're going to try to derive a formula that does not have the derivative. So how do we do it? We do it by analyzing the relation of the function. So what we're gonna do here is to look at how it's being defined. The denominator is the price function, numerator is a derivative of the price function. If we have continuous compounding model, then the discount factor is e to the negative delta t. Therefore, derivative of the price function would be the derivative ct times the derivative e to the negative delta t. That is t times e to the negative delta t. Realize that in this entire model, the derivative is I, but for the continuous compound model, the independent variable is no longer I, is actually the little delta. Okay, so the delta in the numerator and denominator, they are the independent variable. That's why the t become a coefficient. When you're differentiating e to the negative delta t with respect to delta, you have e to the negative delta times t, since t is according to chain rule, t is a coefficient that we have to multiply. So anyway, think of the denominator as a present value of the cash flow, and think of it as a known coefficient. Okay, so we call that PI. So the cash flow CT times 1 plus I to the power negative T is being divided by PI. So CT is a discounted cash flow of a future cash flow discounted to present time. PI is a total present value. So in the last line of the formula, CT 1 plus I to the power negative over PI, it's like a weight of that present value. One single present value divided by the total present value, that is the weight of that cash flow. And then you multiply by T. So then in a way, the Macaulay duration can be think of it as a weighted average of the time, since it's a summation of the t, with t having a coefficient that represented the weight of a certain future cash flow, discounted to present time. All right, so according to this formula, especially the last line, we're able to get a conceptual understanding of the Macaulay duration. Macaulay duration of a set of cash flow is a weighted average of a payment times weighted average of those t at which the cash flow occur. If the cash flow at time t is Ct, the weight given to the time t is Ct 1 plus I to the power negative t over Pi, the proportion of the total price attributed to the time t cash flow. So this is one of the understanding of the Macaulay duration. And so then future, when you try to analyze Macaulay duration, one of the ways is using Excel spreadsheets. Because with Excel spreadsheet, the total present value can be calculated quickly by adding each of the discounted future value to present time, discounted to present time. Okay, this is a example about duration of zero coupon bond. You can see that duration of zero coupon bond, its duration is equal to the maturity. Okay, N-year zero coupon bond is purchased to provide an annual effective yield I. So we're gonna find the Macaulay duration DI infinity and the modified duration DI1. The bond has a single cash flow at its redemption, so there's only one cash flow. So then the weight is like total weight is 1, and therefore the time is the only cash flow time that will be the maturity n. So it's Macaulay duration di infinity equal to n. N will be the number of years of the n year zero coupon bond n. All right, so it's modified duration, we need to take the Macaulay duration divided by 1 plus I, because the Macaulay duration equal to the modified duration times 1 plus I. So the modified duration equal to the Macaulay duration divided by 1 plus I. Okay, so how do we calculate duration of a coupon bond? For zero coupon bond, the maturity is the Macaulay duration. But if we get a coupon, then do I have a solution here? We do have the solution. So it has coupon, and we can do this with Excel, or you can use this formula. Okay, so we can actually calculate this using a spreadsheet. So according to what we're mentioning here, we need to know time of the cash flow and also the actual cash flow and then the present value of the cash flow. 10-year, 8% with semi-annual coupon. So the time 0, semi-annual 0.5, semi-annual coupon time 1. Instead of doing that, maybe I'll just use a formula. Okay, so these are all time, and it's a 10-year coupon bond. So we're gonna drag this down to 10-year, and it's already 10 times 10. 10 is maturity. 8% bond. So if it's 8% bond and the face value is 1500 times semi-annual coupon is 0.04. I mean, 8% is a whole year. Semi-annual would be 4%. Um, so what is that? Is that value 600? So we're getting 600 every 6 months. So that would be all right. But at maturity, it's at maturity 15,000. So then at maturity we add the 15,000 to the coupon. All right, and we need to find its present value. So the redemption amount is 16500. So the face value does not equal to the redemption amount. The redemption amount is 16500. I did it wrong here. So we're gonna do 16500 plus the 600. I didn't copy it. Okay, so right here is gonna be 17100. All right, and then we now need to find its present value. Um, 8% coupon bond. What was the interest rate? The coupon rate is 8%, then oh, it says D 1.02 squared minus 1. That's the I. That is the I. So the annual effective interest rate is 0.3. Okay, so the 600 will be discounted by 1.03 to the power of 1. And how do we make it more general? Okay, so we're gonna do the same. So we're gonna discount every single one. All right. So the total present value is gonna be the summation of this. So you would have summation of the entire column. I want to find the weight for each present value of the cash flow. Um, that's the total present value. And then we need to note weighted average of the time. So the weight is gonna be the cash flow is in C3 divided by the total that is in C23. That is the weight. So we're gonna find the weight for every cash flow here. Okay, now we are gonna, it's a weighted average of the time. So we're gonna take the time, multiply by the weight. So we're gonna multiply A3 with D3. And we do the same. And here we're gonna find the summation of them. That's our Macaulay duration. So we're gonna add from E3 to E22. That's Macaulay duration is a little less than 5. Well, what was the duration here? It was a 10-year. Um, that's not right. 7.4. Total present value is 7.4. Um, A22. 600 times 1.3. Mm, 6500 is 1650 is the last cash flow. The time divided by 2 because it's semi-annual payment. Total present value is this. Um, 600 is the cash. Um, it seems to have the wrong present value calculation. -20. Why is this 600? It's okay. Um, it's supposed to be, no wonder, it's supposed to be 1, 7. It's supposed to be whatever in B22. Oh, no wonder. So the total, I did it wrong for time, for the expiration time, because I did the fill down function, but it's supposed to be what's in B22 being discounted for the present time. So this is total present value. The method itself is okay. I should watch out for high enter data. This is a modified duration, the Macaulay duration, Macaulay duration, which is equal to what's in E23. And to find modified duration, you take it divided by the interest rate, so it's equal to what's in F25 and divided by 1.03 that we have earlier. So this is the modified duration. And that's see, making a mistake is easier. Finding the mistake often takes time. So that's the the PowerPoint that I was posting. But let's focus on a couple of more example on duration. Made a separate PowerPoint for this. Basically, duration tells us how much the price might change when the interest rate change. And as you can see, it's kind of like the derivative function of the price function divided by the price function itself. It measures the sensitivity of the price function to the interest rate change. Okay, so for example, the price of a bond with duration 5 will increase or decrease by 5% when the interest rate moved by 1%. We did define Macaulay duration and modified duration. They're very similar. If you are able to calculate Macaulay duration, all you have to do is to divide by 1 plus I to get the modified duration. And here is the example, just to illustrate the point that the modified duration, Macaulay duration, is actually weighted average of the time. So what we're going to do is suppose we have a cash flow as here, it's a coupon bond. So the expiration, the face value is 1,000 and the not exactly a coupon bond. This is a cash flow. So I have a cash flow of 10 at time 1, cash flow of 20 at time 2, and cash flow of 1,030 at time 3. When I find the Macaulay duration, you should find something close to 3 since the expiration is 3. And the biggest cash flow is at time 3. So what we're going to do is we first want to find the average time. So we would find the total cash flow and find its weight of each cash flow in relation to the cash flow. So this is a way to find the weighted average of the time, but this is not the actual Macaulay duration. What's the actual Macaulay duration? Is to find the present value of all these cash flow. So 10 times the v would be 1 plus I to the power of -1. 10 times v plus 20 times v squared plus 1,030 v cubed. That is the total present value. Now, each cash flow is being added in the present value of each cash flow is being added in the present value calculation. Now, each one of these can be divided by PV. Say 10V divided by PV, 20V squared divided by PV, 1,030V cubed divided by PV. That is a weight for each present value of the future cash flow. Now, using that as a way, we time 2, time 1, time 3. 1, 2, 3 are the time of each cash flow. And this is a calculation of Macaulay duration. Um, so just to illustrate the point here, we don't have the I, so we don't know the value of V. If we do have the interest rate I, we would be able to complete the calculation to get the Macaulay duration. That is a lot in the last line, the value T would be the calculation of Macaulay duration. Now, Macaulay duration of a set of payment is the weighted average of the time of the payment. The weight of each payment at time t is equal to the present value of the payment at time t divided by the present value of all the payment. So this is really the the idea of Macaulay duration. So here, we refer back to that example earlier. Suppose the interest rate is 0.03. We will be able to finish calculation of the present value and finish calculation of the Macaulay duration, which gave us 2.96 again. So Macaulay duration for a zero coupon bond will equal to the term, and right, Macaulay duration for a coupon bond, you have to focus on calculating the par value bond would equal to a NIM. That is interesting. Present value calculation of the annuity immediate. All right, how do we calculate Macaulay duration for a portfolio of assets? Suppose we get a portfolio which involves three different bonds. Bond A has a price of 2,000, a Macaulay duration of 9.5. Bond B have a price of 3,000, a Macaulay duration of 9. Bond C has a price of 5,000, a Macaulay duration of 16. So now the question is, um, we want to determine the Macaulay duration of the portfolio using annual effective rate of 6%. So suppose that everything here is in our portfolio and we want to calculate the Macaulay duration. Now this calculation is you're going to combine, theoretically you should be able to find a cash flow for A, B, C. And then you find the weighted average of them. So in a way, you'll find the weighted average of 9.5, 9, and 16. So what we're gonna do is the 2,000 is divided by the total, which is 10,000. 2,000 divided by 10,000, 3,000 divided by 10,000, and 5,000 divided by 10,000. These are the weight of each of the duration. So this Macaulay duration of the portfolio is a weighted average of the Macaulay duration of each asset. We get 12.6. This is the Macaulay duration for the entire portfolio. That's an example about Macaulay duration of a portfolio. Um, So basically, according to that example, the Macaulay duration of portfolio is a weighted average of the Macaulay duration of individual asset. The weight given to the duration of the individual asset being the proportion of the total price attributed to that asset. So here we have duration of a portfolio of bonds. Suppose we have a bond portfolio consists two bonds, 10,000 5-year zero coupon bond and 2,000 6% par value 2-year bond with semi-annual coupon. We want to calculate Macaulay duration of the portfolio at the interest rate of 0.45. Number one, and the zero coupon bond duration should be easy to calculate, is 5. The one that has coupon we'll find its we'll find the present value of all the cash flow, and then we're gonna discount each cash flow. So each cash flow is discounted, and then we find Macaulay duration for the 2-year coupon bond using the discounted cash flow weighted with relative to total present value and multiply by the time. So we get 1.91. That is the Macaulay duration for the 2-year bond. Now we got a portfolio. The 5-year Macaulay duration 5 price is 8,024.51, and then the 2-year, which has a Macaulay duration of 1.9157, it has a present value of 2058.68. Okay, so we find the weighted average of those Macaulay duration of each bond to total Macaulay duration of the total portfolio, which is 4.57, a little close to 5 and to the 2. All right, so basic modified duration equal to Macaulay duration divided by 1 plus I being the effective interest rate for each cash flow, and modified duration also equal to negative P prime I divided by PI. That is the same definition as in the book. So one definition using the derivative, one definition is using Macaulay durations. Macaulay durations can be calculated with or without the derivative function. Um, Here we have a little example. Around the purchase of perpetuity, providing a payment of 1 at the beginning of each year, the perpetuity's Macaulay duration is 30 years. Calculate the modified duration of this perpetuity. Now, the modified perpetuity is Macaulay duration divided by 1 plus I. Then the Macaulay duration is 30. So 30 divided by 1 plus I. And what was the I here? We got to calculate the I for the Macaulay duration of a perpetuity is 1 over I. Since we know that equal to 30, then I equal to 1 over 30. So Macaulay duration is 30. 30 divided by 1 plus 1 over 30. That's how we calculate the modified duration. So in the last line of calculation, modified duration equal to Macaulay duration, which is 30, over 1 plus I, the I equal to 1 over 30. And with that, we can finish this question. The example in here, one thing we did not talk about more is the convexity. The modified convexity equal to the second derivative function of the price function divided by the price function. So Macaulay convexity C I infinity of a set of cash flow is a weighted average of the square of the time at which the cash flow occur. If the cash flow at time t is Ct, the weight given to t squared is Ct 1 plus I to the power negative t divided by Pi, the proportion of the total price attribute to the time t as time t cash flow. Same weight as what's used in computing the Macaulay duration. So Macaulay convexity is really the weighted average of t squared. Okay, so that gives us a hint on how do we calculate a convexity if we were to calculate it using a set of cash flow. Now, Macaulay convexity for a portfolio is a weighted average of the Macaulay convexity of individual asset, the weight given to the convexity of individual asset being the proportion of the total price attributed to that asset. So very similar to the Macaulay duration, except this is weighted average of the t squared, weighted average of the Macaulay duration, the Macaulay convexity is the weighted average of t time. All right, so that is a review of some of the major concept. If you got a question for any example that we had, please let me know. Another thing we want to mention is immunization. If we haven't had enough example, let's use this file to review. So here we have a company have a liability of 72900 due in 2 years. They wish to immunize this liability at interest rate that correspond to annual discount factor of V equal to 0.9. Okay, so all discount factor can be converted to interest rate. So if V equal to 0.9, then 1 plus I equal to 1 over zero point 0.9, I equal to 1 over zero point 0.9 minus 1. So that's our interest rate I. But using V, we can also calculate present value, future value, and so on. Using a 1-year zero coupon bond and a 3-year zero coupon bond, determine how much of the 1 and 3-year bond should be bought. Now, zero coupon bond, their maturity is their duration. So assume the face value of the bond is A and B. Now, on one part, the present value of the asset would equal to A times V is a 1-year bond, so it's discounted for 1 year, so AV. Now B is a 3-year bond, so it's discounted for 3 years, so BV3. A equal to 72900 is the future value discounted for 2 year. We need it for 2 year. So the total present value of the cash flow A and B should equal to the total present value of the 72900. And that is matching the present value. Number two, we were supposed to match their duration. Now, duration for A and B, they're 1 and 3. Duration for the 72900 is 2. Okay, so basically for that, so we got AV plus 3B V3. So that divided by the total present value, which is AV BV cube. And that is a weighted average of 1 and 3. And that should equal to 2 since the 72900 is due in 2 years. So we needed the duration to equal to 2. So the combination of duration of the duration of the portfolio with A and B should equal to the duration of the liability. Duration of liability is 2. Duration of the asset, we will match that. So with that, we get a little formula. So we got equation 1 and equation 2. With this 2, we're able to solve for A and B. That is the idea in this question. All right. So if there's a asset on each side of the liability and 1 and 2 are satisfied, the full immunization is achieved. So in this question, we got 1 and 2. If you're satisfied equal present value and equal duration, we call that having a full immunization. If there's a liability on each side of the asset, then the immunization cannot be achieved. Okay, so basically we could have asset on each side of the both side of liability, which is what we're doing. The liability is 2, it's at time 2. Asset is at time 1 and time 3. And now we're able to achieve full immunization. But if we have A in the middle, L at either side, here we have the decision we see that liability on each side of the asset, A at middle, L, L1, L2 at either side, then we cannot have immunization. We cannot have full immunization. That cannot be done, or we can say there's no solution to it. All right. Let's talk about SI. SI is the price difference between asset and liability. Okay, so This is about the Reddington immunization in our book. If we match the asset and the liability, their total present value should be equal. So SI 0 would equal to 0. And if we match their duration, then S prime I 0 should equal to 0. Another thing is as the asset should have higher second derivative than the liability. So then the S second derivative is positive. This is the reasoning behind the formula 9.6.2. So here we mentioned the Reddington immunization. If the condition 9.6.2 holds, then the yield curve and also the yield curve is flat. Um, we'll see that Si plus H is higher than 0, so then the total for smaller h, basically we have the present value of the asset will always be higher than the present value of the liability. That means we will always have ability to pay for the liability. We have enough asset to cover the liability. Condition 9.6.2 is equivalent to the asset and liability having equal present value, equal Macaulay duration, and the Macaulay convexity of the asset being larger than the Macaulay convexity of the liability. That actually brings back to uh, the full immunization. So for full immunization, we match the present value and we also match the duration. For Reddington immunization, we actually require matching present value, matching liability, matching duration, and also second derivative got to be positive. Okay, so Reddington immunization does have a little bit more requirement than the full immunization. All right, so here we have a little question, a little example. Allen and Peabody Insurance is obligated to make a payment of 122,000 in exactly 4 years. In order to provide for this obligation, their financial officer decides to purchase a combination of 2 year zero bond and 5 year zero coupon bond. Each of these is sold to yield an annual effective yield of 4.5%. How much of each type of bond should purchase so that together the 120,000 outflow in 4 years and the zero coupon bond constitute a portfolio certified Reddington immunization. Condition 9.6.2 at annual effective rate of. Okay, so how does this immunization help? So in this case, we're gonna have suppose we get the first bond and second bond, their A and B are how much we purchase. We purchase the A and B should be the present value. So A plus B, well, we are the face value for both bond together should equal to the discounted present value of the 120,000. So 120,000 discounted to present time should equal to A plus B. And also this is matching their present value. And then we're gonna match their duration. The 2 year bond and 5 year bond, they're zero coupon bonds, so then their duration is their maturity time. So we're gonna find the weighted average of 2 and 5. 2 is for asset A, so A over A plus B is the weight of 2. The weight for B is B over A plus B, and this total supposed equal to 4. And as a result of the second equation, we have B equal to 2A. Bring B equal to 2A to the first equation, we can solve A and B. All right, then we're going to talk about the convexity, um, which we calculate convexity for both assets. For this assets that we had in duration in 4 years. So duration for the 120,000 is duration equal to 4. Now duration for Yeah, that's the duration. Convexity of this is a square of 4. So 4 squared is 16. And then we're going to need to find the convexity of the portfolio. So we're going to square the there are 2-year bond and 5-year bond. So 2 squared is 4 and 5 squared is 25. So we're going to find a weighted average of 4 and 25. So the asset A over A plus B times 4, and then asset B 67084 over the 1627. That's the weight for 25. So we get 18. So the convexity of the portfolio, which is convexity of the asset, is higher than the convexity of the liability, which is 16. All right, so that's that. A little bit about the full immunization. Suppose the delta zero denote the current force of interest. I suppose the portfolio consists of a single liability to be paid at time t, along with a pair of asset U and W to be paid at time t minus U and t plus W, respectively. So, like I said, if you have a liability in the middle, earlier and later asset, this full immunization can be done. But if you have a asset in the middle, liability on both sides, that cannot be done. So looking at this situation here, um, so we do have requirements. Further, suppose that the net present value S delta zero of the portfolio is zero, net present value equal to zero. That means liability and the asset have the same present value. The derivative also equal to zero. That means they do have the same duration. Then if the delta is not equal to delta zero, net present value S delta is positive. So that's something we get. That is saying if the liability and asset are in this order, then we can always count on the full immunization. And that means the difference between asset and liability will always be positive. That means you can always cover your liability with your asset. Um, so this is a little explanation of the reason for it. This is a practice question. Overall, I think this counts as a review of immunization and duration. Immunization is a way to immune to interest rate risks. And this is something we always aim for with financial management. If you got further question, please let me know. I hope that can kind of serve as a review for chapter 9.